Hello viewers and welcome back to this channel. So in this video, we're going to be proceeding with our organic chemistry series. So this video is going to be involving coverage of organic chemistry, and it's going to be specifically applied organic chemistry. So this video is presented to you by Yusuf. You advise after watching the video, share it to your colleagues so that you can help us as a team. So with this, we are going to start with soaps together with soapless detergents. So this video is going to be specifically handling soaps and soapless detergents. And the second video, we are going to be covering polymerization. And after that, we shall be concluding applied organic chemistry with the third video. So under this video, we are going to start by soaps, looking at the advantages over soapless detergents. We also look at the cleansing action of either of the two. So when you look at soap, we can define soap as a sodium or potassium salt of a long-chain carboxylic acid. So sometimes we bring this definition in mocks. That's why I decided to present this video as early as possible. So soap is simply a sodium or potassium salt of a long-chain carboxylic acid. So we can add on that by saying soaps are going to be obtained from vegetable oils or natural fats, which can also be known as glycerides. So the glycerides of what you can refer to as fats are going to be esters of a triol, which is the same as an alcohol, a trialcohol, and this alcohol in this case is going to be called glycerol. Or the other name for glycerols can be called propan 1,2,3-triol. So this A on this name is not present. So it can be called propan 1,2,3-triol. Remember, when you're naming organic compounds, we separate numbers by commas, and then we separate letters from figures by hyphens. So it can also be called propan 1,2,3-triol, and then the long chain carboxylic acids are also going to be united to it so that you can form our glyceride. So for us to get glyceride, we need to combine 1 molecule of glycerol together with 3 molecules of a carboxylic acid, of a long chain carboxylic acid. Then later we end up with getting our glyceride. So a molecule of glycerol, if you are told you're doing biology, I'm well aware you have already covered this in chemicals of life because you have emphasized this, and it's highly examinable under objectives. So if you get glycerol, 1 molecule of glycerol combines with 3 molecules of long chain carboxylic acids for us to get our glyceride molecule together with 3 water molecules, since it's a condensation reaction. So with that, we can proceed by saying that the carboxylic acid used to obtain these glycerides are going to usually be saturated, and they have enough number of carbon atoms. That's why we call them long chain carboxylic acids. That means that the carbon to hydrogen ratio must be as high as possible, probably or preferably between 12 to 20 carbon atoms. So with that, we can look at some of the examples of long-chain carboxylic acids together with their formulas. Here we give their names. Their names are going to depend on the number of carbon atoms held. For that one that has 12 carbon atoms, it's going to be called dodecanoic acid, since it's a carboxylic acid. All carboxylic acid have a prefix of OIC at their end. So if at all you're having 18 carbon atoms, which is the common one, you are going to have octadecanoic acid, which can also be called stearic acid. And this one is going to have 18 carbon atoms. So for 18 carbon atoms, it's going to be represented by the following formula. What you have to ensure is that you have to first write the carboxylic group at the end, and then you find a way of writing other carbon atoms in terms of the R group on the other side, which is the left hand side. Similar applies to the first option. So by formula or the formula of the glyceride, after each of these carboxylic acid combining with long chain carboxylic After each of these long chain carboxylic acid combining with glycerol to form a glyceride, they are going to form the following products, which we refer to as which are going to be used in the manufacture of our soap. So glyceride, we here in the brackets I say that glyceride here it can be used to form the soap that this topic is about. So this one is called hexadecanoic because we're having 6 carbon atoms, which can also be called parametric acid. So it's represented by this formula, and after 3 molecules of this carboxylic acid combining with glycerol, we end up with this glyceride, and this glyceride later in turn we use it to form our soap. So with this we are saying that any of the above glyceride or fats can be used to manufacture or to make soap. So fats are going to be solids and they are going to be mainly saturated at room temperature. So they can be obtained, we can obtain fats from coconuts. I hope every one of you knows this fruit. Also, if at all we have not used fats to manufacture our soaps, we can use vegetable oils. Now, vegetable oils, for them, they are liquid at room temperature and they are also highly unsaturated. I hope your practical teachers or the laboratory practicals that you have done, they have shown you how unsaturated compounds behave. So later we shall try to organize a practical session via this channel. So you're saying that samples of vegetable oils can be got from the following materials. So first we can get it from cottonseed oil, simsim oil, groundnut oil, sunflower oil, palm oil, or cashew nut oil. Now if you are being asked for the raw materials from which soap is manufactured, there are only 2. We are having what we call animal fat together with vegetable oils. So we are going to look at how we can use each of them to obtain soap. But mainly this one is the most friendly in case it comes to answering questions because it gives you a wide range of answering questions. If at all you are being given the sources from which it comes from, I gave you a wide range of examples. So starting with animal fat, you're going to say that the animal tissue is heated with water. So the fat melts and floats on top of the surface of the hot water, and after that, the molten fat is then skimmed off into a separate container whereby it is allowed to cool until it solidifies. So that's how we use animal fat in getting, that's how we extract animal fat. That's not how we prepare soap, that's how we are going to extract it. That's why we say that extraction of these 2 raw materials, both animal fat together with vegetable oils. So, but when you're answering these questions, you're not supposed to be as accurate as possible. This is applied chemistry. So you can simply explain in a way that you have understood this sentence. So someone else can say that an animal tissue is got from, let me say, the butcher's place and placed in boiling water. After we wait for it to melt and we skim off the fat that has felt on top of the water, which is later put in a separate container and allowed to cool, and therefore animal fat is extracted. So you are allowed to use any language which is friendly to you, and that's why applied organic chemistry is very easy to pass as compared to the theoretical organic chemistry. Now let's also look at how you can extract vegetable oils. Now I've gave you a range of examples from which you can extract vegetable oils, but the most practical ones, especially for people in villages or in rural areas, or whichever area you are in, majority of you at least have tried to extract oils from groundnut seeds. And this is especially by making this dish, which is called odi by northern Ugandans, or what is also known as shipoli in the central region. So this is where we get the oil that comes out is what we call the vegetable oil. That oil can be used as a raw material in the manufacture of soap. So you can say that here we are going to say that the dried seeds, groundnut seeds are got and they are dried. So the dried seeds are going to be roasted and then they are going to be crushed to obtain a paste. You describe the same way you manufacture that thing, that OD which you have already made at home with mom, or which you have already made out for yourself. So this paste is going to be added to water and then the mixture boiled until oil floats on top of the surface or on top of the mixture, the paste together with the water. Now after oil floating on top of that mixture is going to be decanted off. Decanting means that you separate off that layer which has floated on top of the water or on top of the mixture that we don't need. So the oil layer which has floated on top is going to be decanted off into a separate container. So now we are going to be proceeding to the preparation of our soap. Since we have seen how we can extract the raw materials that are required in the preparation of soap. So now let's look at the procedure from which now we can use the raw materials that you have seen in preparation of our soap. So the raw materials for preparation of soap is either going to be animal fat together with vegetable oils. But usually in an examination, we tell you to state either of one. So you're not supposed to state both of them. So if you either go with animal fat, you go with animal fat. If you either go with vegetable oil, you go with vegetable oil. You pick the raw material from which you can easily get a range of description or a range of application. The most convenient one in passing is vegetable oils. But also animal fat is not that hard because you just have to buy the tissue from the butcher, cook it, let it float, let the fat float and skim it off and put it in a separate container for it to dry. So now when you to operate the procedure, we are going to say that the vegetable oil or the animal fat that you have already extracted is going to be boiled with concentrated sodium hydroxide solution. And this is going to be done while stirring this vegetable oil or fat until it completely dissolves in our base, which is concentrated sodium hydroxide solution. So after that, the solution is going to be cooled and then the concentrated brine. Remember that brine is the same as concentrated sodium chloride solution. So the solution is cooled and then concentrated sodium chloride is going to be added to precipitate this soap. Now, for some of you may be asking, how is this brine causing the precipitation of the soap? If you remember in ionic equilibria or in ionic chemistry, when we are looking at common ion effect, the reaction between the animal fat together with, or the vegetable oil together with the sodium hydroxide is going to be an equilibrium reaction. And if at all, since we are adding sodium chloride as another solvent or as another reagent, is containing a common ion to that of sodium, which is already present in solution. So what happens is that this is going to increase precipitation of our salt via the knowledge of common ion effect in chemical equilibrium. But since we are in organic chemistry, let's keep everything simplified. So after you dissolving your animal fat or vegetable oil with concentrated sodium hydroxide solution, we add brine or you add concentrated sodium chloride solution, and this is done to precipitate our soap. Now after soap precipitates, it's going to float and it's going to be skimmed off, and therefore this process can be done. The skimmed off product can be processed into bars or soap powder, any form that you want. So the general equation for that is going to be the following. So this is going to be your glyceride. Remember that this is going to be either your animal fat or your vegetable oil. So always it's going to combine with 3 molecules of a base, which is going to be 3 molecules of sodium hydroxide. Do not forget this. Always your animal fat combines with 3 molecules of sodium hydroxide. The reason I'm putting an emphasis here is because you need this equation in case we set a calculation number about it. So after that, you get your glycerol and then you get your long chain carboxylic, your sodium salt over long chain carboxylic acid, which is the same as soap, and it must be solid in nature. So you're going to say that where R is a long chain alkyl group, you put an inverted V here and say where R is a long chain alkyl group. So with that, we are going to make some note that glycerol is a variable product because in the manufacture of nitroglycerin, which is a constituent of many explosives, glycerol is going to be used in the manufacture of plastics. Now, there's no need to master this You may just say glycerol is used in the manufacture of plastics. Now, why did I know this? It's because when you're setting organic applied chemistry, at the end of the question, we are always going to ask you for the importance of what you are preparing, or the importance of what you're intending to prepare. For example, if you're dealing with soap, how are the products from soap going to be used? If at all soap is used at home for doing laundry, then what about other products when you're manufacturing soap, such as glycerol? What are they going to be used for? And this is the purpose of this note. So glycerol is going to be used in the manufacture of plastics. Also, the sodium salts or the sodium soaps have limited solubility in water, and therefore they can be obtained as solid cakes, whereas the potassium soaps are more soluble and they can be used as gels in shampoos together with shaving creams. So here a question may be framed that state why potassium soaps, long chain carboxylic acids or potassium, or soaps made of potassium are more useful as compared to soaps made of sodium. So the reason for that is because the solubility for potassium soaps is more higher as compared to the solubility for sodium soaps, and therefore potassium soaps are going to be preferred in manufacture of liquid liquid soaps, such as liquid soapy products such as shampoos that you use to clean your hair, and also shaving creams that you may apply when you're cleaning your private parts. So going to parts, you are going to say that if at all the glyceride is used is going to be specified, then the equation for the reaction is going to be specified by R. For example, if at all assuming that this is going to be your glyceride, and then always it combines with 3 molecules of sodium hydroxide to get the first product that you get before getting soap is going to be glycerol, and then later soap is going to be precipitating out slowly. But you should not hear that you're having 3 molecules of sodium hydroxide to give you 3 molecules of our soap or our long chain sodium carboxylic chain. If you look at part D or note D, we are saying that if the mass of glyceride used is known, then we can calculate the mass of the soap that is going to be formed. For example, let's look at the example below. So looking at this worked example, we say that soap was prepared from 96.65 of a fat. Now this 96.65 is in grams. You put here cursor and you say grams. So soap was prepared from 96.65 grams of a fat, mainly derived from octadecanoic acid, and we gave the formulas for this. So 1, you are going to write an equation for the reaction leading to the formation of the soap, and then part B, you calculate for the mass of the soap that is going to be formed after complete reaction. So first things first, we combine our glyceride with 3 molecules of sodium hydroxide, and we also form 3 molecules of our long chain sodium salt, which is our soap. And the product, the first number 1 product, you should always remember that it must be glycerol with this formula. You make sure that you practice these things. And glycerol is a liquid, soap must be a solid. Now if you look here, the glycerol molecule is always this side. If you look here, this is going to be a glycerol molecule, and this glycerol molecule has combined to a chain of the octadecanoic acid. So you must make sure that if you remove this branch of glycerol, you remain with 18 carbon atoms, because that's what octa means, octadecanoic. That means that you're having 18 carbon atoms. So if you look here, this is going to be 1 plus this 16 plus this 1 here, and they're going to sum up to 18, together with your carbonyl-carbon group attached to the glycerol molecule. So they combine, these two combine, just like you saw in the previous example, they combine as a condensation reaction. That means that their combination, like you explained in biology, chemicals of life, is going to give off some waters of molecule. So we form a product like this. So after that being said, we're going to proceed. So this is the equation, or this is the main equation, and this is going to carry 1.5 marks, but mainly it's going to carry 2 marks for the case of applied organic chemistry. So if you look at, they're telling us to calculate for the mass of the soap that is formed after complete reaction. When they talk about complete reaction, we have to refer to the equation. And in the equation, we always use moles. That means that we have to get this mass that was given, and then we convert it to moles. So for us to convert mass to moles, we have to first get the mass of this ester that we're having. So it's going to be carbon. So it's going to be 12 times 19 times 3. And this is going to be for carbon, calculating for the mass of carbon. Then oxygen is going to be 16 times 2 times 3. Now this 3 is common. You'll see this 3 repeating because we are having 3 chains. Then later we are going to have 37 multiplied by 2, then plus 36 times 1. So all this one is going to be, this is the way I calculated for the molecular mass of all this. But you can calculate, this is for hydrogen, this is for oxygen, and then this is for carbon. So if you look here, in each and every chain, I'm having 19 carbon atoms. And then this is the relative atomic mass. And then this is the number of chains I'm having. The same thing, if you look here, oxygen, you're going to observe the same thing. So oxygen, I'm having 2 in each and every chain. In one chain, I'm having 2. And also oxygen atoms, relative atomic mass is 16, then times 3. Same applies to hydrogen. So if you sum them up, if you count everything up, you're going to end up with a total relative formula mass of 890. If you say RFM, don't put units. If you say molar mass, you put units in terms of grams. So for us to convert this given mass to moles, we are going to say the number of moles of the ester that are going to be used is going to be 96.95 divided by 890, and this is going to end you up to 0.108933. So let's proceed with the calculation, and this is how we can obtain this mass of the soap that is going to be formed after reaction. That means that you have to compare, since we're having now the mass of the glyceride that is used, we have to compare this one together with this one. So from the equation, you can see that 1 mole of the glyceride formed 3 moles of the salt. What about these moles of glyceride? Just like I've explained, 1 mole of the ester formed 3 moles of the soap. What about the moles that you have calculated above? So it's going to be 0.108933 multiplied by 3 divided by 1, and this is going to be moles of the soap, and you're going to end up with this. So since this is moles of the soap, now we need to convert the moles of the soap back to grams. So for us to do that, remember that RFM 1 mole weighs the RFM of any substance. Then what about these moles? So we have to get the RFM of our soap by doing the same calculations. You count the number of carbon atoms you're having, you also count the number of oxygen atoms you're having, you count the number of hydrogen atoms together with the number of sodium atoms, and then you're going to end up with a mass or a molar mass of soap to be 306 grams. So using that knowledge that 1 mole weighs this, what about these moles? You're going to end up with the mass of soap being 306 multiplied by 0.326798, and you're going to end up with approximately 100 grams. So with that, let's look at the cleansing action of our soap. So here, soap simply acts by lowering the surface tension between water together with the oil or grease that is present in the tissue, simply by emulsifying them. So with that, we are going to say that the soap molecule is going to have a long chain hydrocarbon tail together with a non-polar. Non-polar means that is not water soluble. And hydrophobic. Hydrophobic means water hating, something that does not dissolve in water. And also a carboxylate group, but this carboxylate group for it is going to be polar and hydrophilic. Hydrophilic means that something that is water loving. So when soap is being added to water, the hydrocarbon tail or the hydrocarbon chain is going to be attracted to the dirt, and then the carboxylate group is going to be attracted to the water. So one is going to be the tail or the hydrocarbon tail is going to go to the dirt in the cloth, and then the carboxylate group is going to be attracted to the water molecule. So by doing this, we create a loop. So that's why we are saying that this reduces the surface tension that is between water together with the dirt, and therefore the oil or grease or dirt particles are going to be removed. This loop here contracts inside, so that the dirt or the grease or the dirt particles that are present within the tissue are removed, and they are going to be suspended in water, which we call emulsification. And this is the whole process of the cleansing action in soap. We give this whole process about 5.5 marks, mainly 5.5 marks, but it can't go below 3 marks at the worst scenario. So make sure that it's a very simple process. It acts by lowering surface tension, whereby your hydrophobic long chain tail is attracted to the dirt, whereas the carboxylate group is attracted to the water, creating a loop that contracts, removing the dirt from the tissue into the water, and that process is called emulsification. What you should note that is that the long hydrocarbon tail or chain is going to be non-polar and hydrophobic. Hydrophobic means water hating, whereas the carboxylate group is always polar and hydrophilic. So you're going to make a note that soap is not effectively used in hard water simply because it forms insoluble calcium or magnesium salts, leading to soap wastage, which in O level you refer to as scum, which is also marked at A level. So we may ask you, usually this is a very common question, why soap is not eligible or is not advisable in usage of soap under normal circumstances as compared to, let's say, soapless detergents. So soap usually forms scum, leading to soap wastage. Scum is the same as insoluble source of calcium or magnesium, which can be represented by this equation. So leather, which is that white component that you see when you're washing either utensils or clothes, leather can only be formed when all the magnesium ions or when all the scum is completely precipitated, or when all the magnesium ions together with the calcium ions are completely precipitated as scum. Now with that, let's also look at this note B. Now this note B, usually we bring it in explanation questions in paper 2. Explain why it's not advisable to use soap in washing aluminium utensils. Now this is a part, or this should be, to understand this you must have covered ionic equilibrium knowledge. So if you look at ionic equilibrium knowledge under salt hydrolysis, you have seen that salts are long-chain hydrocarbon chains of sodium ions. So in solution or when exposed to aqueous conditions, the sodium ions together with the chain separate and then we remain with this. So if at all, now remember that is soap. Your soap is composed of this ion when it is dissolved in solution. So what happens is that soap undergoes hydrolysis. When it undergoes hydrolysis, we form these compounds. So with that, we're going to say that soap is not recommendable for continuous usage when washing aluminium utensils, since the soap is a solid that is made from a strong base and a weak organic acid, it therefore undergoes hydrolysis in solution. So the salt chain undergoes hydrolysis, and this is an ionic hydrolysis, forming a carboxylic group together with hydroxyl ions in solution. Now the hydroxyl ions are going to react with aluminium ions. Remember that aluminium is amphoteric, therefore aluminium is going to react with both acidic and basic conditions or solutions. So aluminium being amphoteric reacts with hydroxyl ions, forming aluminate ions, together with hydrogen gas. Now remember that this is a saucepan. So soap is creating a carboxylic acid which is reacting with a layer of this saucepan. The more it reacts with it, the more it causes wearing of this utensil. So we shall end up with the general equation of hydrolysis to be in this format. So the hydrolysis equation, remember that this was covered under ionic chemistry. I show you how to derive all these hydrolysis equations. And they come about by eliminating, just like we did redox reactions. For this case, you just eliminate the hydroxonium ions. So if at all this undergoes hydrolysis, this carboxylic acid reacts with a layer of your aluminum saucepan. So this causes wearing until that saucepan starts to get holes at the bottom. Mainly at the bottom, you have seen those saucepans. So we shall end up with a general equation for wearing out of those utensils, forming a complex. And therefore, by forming this, we are saying that this saucepan is wearing out. So looking at note at part C, we are going to say that soaps with longer alkyl chains are more effective than those with shorter alkyl chains. So for example, if you look at sodium octadecanoate, it's also going to be called sodium stearate. It's going to be more effective as compared to sodium dodecanoate. So here we are simply meaning that soaps that are of longer alkyl chains are going to be more easier to use as compared to those ones with shorter alkyl chains. So now that was the coverage with the soaps as detergents. So let's look at soapless detergents, and this is going to involve the one that are going to be in powder format, mainly Magic, Omo, together with any other form of reagents you have ever used, together with Nomi. So soapless detergents, by definition, are going to be sodium salts of alkyl benzene sulfonic acids, or sodium salts of long chain alkyl hydrogen sulfate compounds. So the general structure for these soapless detergents are going to be represented by the following, but mainly I encourage you to use this one. In case you're being examined, you may ignore this one, though it looks correct, but mainly master usage of this one, because here we are focused at having an aromatic compound. That's why here we also told you it must be a long chain salt of alkyl hydrogen sulfate. So here where R is going to be the alkyl group. So unlike soaps, soapless detergents have the sulfonate group, which is present in the alkyl benzene sulfonates, and also a sulfate group which is present in the aliphatic alkyl hydrogen sulfates, instead of the carboxylate group as we saw in the soaps. So therefore, detergents are going to be more effective even during hard water, because for them, the corresponding magnesium and calcium salts formed are going to be soluble as compared to the soap which is not, in which they are not soluble. Remember that soap, we have told you that it forms scum due to precipitation of calcium or magnesium salts. But in detergents, formation of scum is impossible. That means that lather is going to be formed quickly, and therefore washing is going to be quite easier if when you're using a detergent or a soapless detergent as compared to a bar of soap. So the equations are going to be as follows, depending on the option that you have decided, but I've told you to opt for number 1. So the benzene sulfonate, alkyl benzene sulfonate sodium salt reacts with the magnesium salt, forming a soluble compound, which must be aqueous, together with the leaving sodium ions in solution. Now with that, let's look at the preparation of the soapless detergents. So part A, the most commonly used detergents are going to be sodium salts of alkyl benzene sulfonic acids, which are going to be made from 1 non-branched alkenes containing 12 to 18 carbon atoms. So let's look at the procedure. So procedure 1, benzene is going to be reacted with the long chain alkene, which is going to be done in presence of an acid, and this is going to be done to obtain alkyl benzene. And after that, the alkyl benzene formed is going to be heated with concentrated sulfuric acid so that we can obtain the sulfonic group on our benzene ring. So that's why we are saying that to form an alkyl benzene sulfonic acid, which is going to be heated with sodium hydroxide solution to form a detergent, or to form our alkyl benzene sulfonate, which is the same as the soapless detergent. And all what you have described, you can represent it in terms of equations. So first you react the benzene ring with an alkene, but this must be done in presence of an acid. This is done to obtain the alkyl benzene. This acid here adds to one of these carbon atoms and then this one becomes a carbocation, which is later, by electrophilic substitution reactions, is added to this benzene ring. After that, we obtain these compounds. So for us to obtain the sulfonate group, we do the sulfonation reaction of the benzene ring. So since this one is on position number, since this one is not a saturated group, it's going to activate either position 2 or position 4. So we want the one of position 4. That's why we went with this one. After getting also sulfonate group on the benzene ring, later we hit with sodium hydroxide in aqueous state to obtain our sodium ion being replaced by the hydrogen atom. And here, this is our soap-less detergent. So sometimes we can ask you to prepare that soap starting from an alcohol. Now here, to prepare that detergent, you need to be very good at organic synthesis. So from here, all you need to do is to make that alcohol an alkene, and then you introduce in your benzene ring together with the acid condition, and then you proceed through with the other steps as you have seen them in the previous slide. So if you look here, the long chain alcohol is going to be heated with excess sodium sulfuric acid to form an alkene. So we get this long chain alcohol, we heat it with concentrated sulfuric acid at 180 degrees Celsius, and these are the reagents that are required to convert an alcohol into an alkene. I hope you are aware about that in organic chemistry. So after forming this one, we are going to get this alkene, and then in presence of an acid, we treat it with benzene ring so that you can proceed with the other steps after forming the alkyl group or after getting the alkyl group onto the benzene. We shall proceed to sulfonation. After sulfonation, we heat with aqueous sodium hydroxide to obtain our detergent in the final step. So that's the procedure that you can follow in case you're starting from an alcohol. So looking at option 3, we can also get it from an alkyl halide. So getting it from an alkyl halide, we make sure that we heat it in presence of an halogen carrier. Like I said, you must be very good at organic chemistry. So you get that alkyl halide and then you put it in presence of an halogen carrier such as aluminum chloride or iron-3 bromide. And later you heat it with benzene to form alkyl benzene. So the alkyl benzene is going to be treated following the other steps of sulfonation together with heating with sodium hydroxide to get your detergent, which I have just given above. We gave the main equation, that's why I'm just referring you to part A Roman number 1, which was of the formation of that detergent. So you get your alkyl halide, you heat it in presence of an halogen carrier. Now sometimes we tell you to heat at 50 degrees Celsius, but also this reaction can take place at 0 degrees at room temperature. That's why you don't put any condition. But for the benzene ring, it's better to put 50 degrees Celsius. But you can ignore, you will also be marked. So this is the product that you're going to end up with. So here we are saying that detergents that are going to be in the form of sodium salts of long chain alkyl hydrogen sulfates are going to be prepared by the procedure described below. But I will not encourage this procedure, like I've said. Always opt for the one with the benzene ring because for it it's easy to manufacture. However, also as a student, if you're good at mastering both, you can also offer this alternative route. However, they are all the same things, so I won't mention too much onto it. First, you get your long chain alcohol, heat it with concentrated sulfuric acid. This must be done at below 140 degrees Celsius to get your hydrogen sulfonate. Then later, we replace this hydrogen atom by simply heating it with sodium or by simply introducing sodium hydroxide solution. Or sodium metal, either sodium hydroxide solution or sodium metal. So what it does, it replaces this hydrogen atom and then you end up with your salt in the following format. So we are going to know that some additives are going to be added to the detergents for specific uses. For example, now this is a very common last question that we always never miss in case we say it applied organic chemistry. So we always ask you, give give other additives that can be used in the manufacture of either soaps or soapless detergents, stating their function, mainly under soapless detergents. So in soapless detergents, we add sodium sulfate, and this is to increase the bulk of the reagent. In case you buy the reagent, you feel like it's of good weight. So that's because of addition of sodium sulfate. So it's purposely added to just increase the bulk of the detergent. We also add inorganic phosphates, and these inorganic phosphates added are the ones that are going to react with calcium ions in the dirt to form soluble complex of calcium salts. And this is not the case with soap. So for detergents, we are having inorganic phosphates within them that prevent scum from forming. And these inorganic phosphates are the ones that react with the calcium ions to lead formation of soluble salts that prevent formation of scum. And then material number 3, or substance number 3, or detergent number 3 added, or the additive, is going to be sodium proxoborate. Now this sodium proxoborate acts as a bleaching agent. So one, you can add sodium sulfate, you also add inorganic phosphates, you also can add sodium proxoborate. So sodium proxoborate is to act as a bleaching agent. Sodium sulfate is to increase the bulk of the detergent. And then the inorganic phosphates are going to be reacting with the calcium ions in the dirt to form a soluble complexes of calcium ions. Now, just like soaps, also the detergents are going to have what you call the cleansing action. Now, essentially, the procedure or the mechanism of performing or removing the dirt is essentially the same as that of soap. But here, in the soapless detergent molecule, the alkyl benzene group, or the long alkyl chain, is going to be the one which is going to be non-polar and hydrophobic. I've already told you that hydrophobic means water hating. And then the sulfonate group is one which is going to be polar and hydrophilic. So when a soapless detergent is being added to water, the alkyl benzene group is going to be attracted to the dirt in the tissue, and also the sulfonate or sulfate group is going to be attracted to the water. Now this causes a pool which contracts, and then later removing this dirt from the tissue and suspending it into water. That's why we are saying that this reduces the surface tension between the water and the dirt, later suspending the dust particles or the dirt particles into water, which we also refer to as emulsification. And that's what we call the cleansing action of the soap. Still, this one carries marks above 3 to 4.5 in case it's well set. So after looking at that, we are going to be concluding by saying, or by giving the advantages of soaps over reagents. Now, the one advantage of soaps over reagents is that for soaps, when they're used, their byproducts are biodegradable. By saying biodegradable is that they can easily perish away from the environment in case they are used. But for detergents, for them they are unbiodegradable. That means that in case they're used and you pour that water anywhere, let me say near the house, you will start seeing green lichens, which all people who are not in biology, green grass growing on the walls of your house. That's because you poured under that area or near your house water which is containing a detergent. If at all you are using soap only, there's no way such things can grow on that house. So soaps are biodegradable, but detergents are slowly biodegradable. So that means that they take long to perish from the environment. Now, the disadvantage of using soap as compared to detergents is because soap form scum, which are the soluble salts of magnesium or calcium, with hard water, which is unlikely to detergents. But also, detergents have an advantage over soapless detergents have an advantage over soaps, in that the detergents can be used even in hard water, because for them they form soluble salts or soluble complexes of calcium and magnesium salts, and therefore by forming soluble complexes or soluble salts of calcium and magnesium, they do not form scum as compared to soap. So soap forms scum, whereas detergents do not form scum. Now the other advantages these detergents, they form lather quickly. That white component that you see after washing utensils or clothes. So detergents form lather quickly, you can add it as your second option. Detergents form lather quickly, whereas soaps do not form lather quickly. Now the disadvantages detergents have over soap, one of them we have already looked at it, is that they are slowly biodegradable. They take long to pressure from the environment, and hence they can act as environmental pollutants. So also detergents contain inorganic phosphates, which are going to be nutrients for algae growth, which deprives lakes and rivers of oxygen. So not only do they affect the house, but also when you pour them in, when you pour water containing detergents in water bodies, you are going to see that algal grooming on top of the ponds, which is going to be greenish in appearance. That's what we call algae. So if at all that thing over become thick or over the pond, it cuts off oxygen supply to the aquatic organisms in that pond. Now later, the consequences of that is that it's going to lead to suffocation of the aquatic organisms, which can later lead to their death. Now that was it for this video. You are advised to subscribe to the channel, share the video to your friends, and make sure that you all discuss this work as a group so that these items I've taught you stink in your mind. So make sure that you leave a like for the video and subscribe for the upcoming videos. Success in your papers.